Okay, so Justin has a question. What's your question?
Is there any units on this? I know you're a unit nuts. As far as our graph goes?
They're all in meters, I think.
All right, cool.
It's pretty sure. Yeah, that's got to be meters. Yeah, pretty sure it's meters. All right, so where'd that page go? I wanted to go back over to revisit the collision detection. I'm assuming that's still a major hurdle, the collision algorithm. Okay, let me get the link for that.
That's the separating axis theorem that we're using for that?
Right.
Okay.
Pull up this link again. And I apologize. I mean, first of all, I'm thinking, oh, well, linear algebra, all you guys, you're fine. You understand all this dot product stuff. And that was probably not a good assumption. And also, it'd been a long time since I'd looked at it, so I was a little rusty on how it actually works out. So I prepared a little PowerPoint slide here to go over this. Also, it is up on D2L. I just posted it this morning. Okay, so this is the figure from that web page, and I'm trying to use the notation like they are as much as I possibly can. And they talk about two vectors, and they don't use vector notation. They don't put a vector arrow on top of anything or give it a bold or anything. So it's a little hard. They're not real consistent with their notation. But basically, they talk about axis 1, axis 2, axis 3, and axis 4, which have to be perpendicular to the sides of the rectangles. Which, as it turns out, perpendicular to one side of the rectangle is the other side. Okay? So for axis 1 in this case, you can pick either the top, this side connecting the upper left and the upper right, or you can pick the lower left, lower right. It doesn't matter which of the two sides you take, because they're both perpendicular to the other side of the rectangle. Okay? So it doesn't matter whether you choose these 2 points or these 2 points. It doesn't make any difference. So they call that axis 1, and that is a vector. And that vector is created by the difference between the two x and y points of those upper left and upper right. Then they talk about another vector that they call a dot LL, or a dot UR, or b dot UR, or whatever. Okay, so instead of the a dots, I've done an a with a subscript LL, and that is a vector. There's an arrow on top, and that's the vector of the point of the lower left. So that's basically a vector from the origin, wherever that happens to be. And it doesn't actually matter where the origin is respect to this, because in the end, the dot products are going to be with things relative to the vectors with each other. Okay? So wherever the origin is, that's where this vector originates. Okay? Now, they talk about taking the dot product between these two vectors. Okay? And you will recall that the dot product between the two vectors is defined as the product of the magnitude of the two vectors times the cosine of the angle between them. Okay? And in order to visualize that, you can move the two vectors to where their tails are on the same place. Now, it doesn't matter which vector you move or where you move it, but just you put the two tails together, and that angle theta is the angle between those two vectors. Okay? Then, well, if you look at this piece here, ALL cosine theta, that's the hypotenuse times cosine of that angle. That gives you this distance here, right? If you look at a right triangle here. So this distance is ALL cosine theta, the magnitude of ALL cosine theta. That's what that distance is. And that's related through the dot product. That's basically the dot product divided by the magnitude of the other vector. Okay? So this distance here is at the dot product divided by the magnitude of the axis 1. Okay? Now, I am going to call that thing the scalar quantity A dot LL. Okay? Now, that's because they use like a little marker. They mark this point and they say that that's A dot LL, which is confusing in their notation because A dot LL previously they're talking about it as a vector, and now suddenly they're talking about A dot LL as a point. I mean, normally if you think about A dot LL not as the vector, that would be the magnitude of the vector, which is not at all what they're talking about. Okay? So that A dot LL is a distance in my definition. Okay? And it's the distance from the tail of axis 1 to the projection of that vector. Okay? So I'm marking it as a point here, but in the way I'm representing it here, it's the distance along here. And that you get from the dot product and just dividing by the magnitude of the axis. Okay? Now, let me go, what they have in here, this equation is similar to the one I have on my slide, but it's a little different. This one is a vector because this is a dot product. That makes it a scalar. I divide by the square of the magnitude, which is different than mine. I just divide by the magnitude itself. So this thing here is a scalar. And then it's being multiplied by a vector, the axis vector. So this quantity they have is a vector pointing in the same direction as the axis, and its magnitude is proportional to the dot product. Okay? Now, later on, they're going to talk about step 3, where they take a dot product. They need to turn this vector that they have into a scalar. And if instead, if they had just taken what I did, where you look at the distance of that, the projection, the distance of the projection, that's actually the scalar that a scalar we're interested in. Now, they go on the next step and say, well, you have to do some sort of dot product. It doesn't really matter what the dot product is because you need to turn it into a scalar. So there's a lot of different ways you can go about it. My approach is a little bit more intuitive in terms of looking at the distances, but they're not wrong. It's just they're a little bit more confusing because first they turn this thing into a vector and then they turn it into a scalar. Basically, I'm combining step 2 and step 3 by not looking at the vector projection, but rather the scalar distance. This distance, that's the scalar distance of the projection. Like I said, I'm combining steps 2 and step 3 together. Okay? Now what's interesting is when I actually coded it, I went ahead and I did what step 2 and then I did step 3, so I followed their approach, but when I'm coming to explain this to you, I find it a little bit simpler to go this way. Okay, so we've identified this point, ALL, which I'm representing really by the distance from this corner to that point. Okay? Now, I'm going to keep axis the same, and I handled this point right here. Now I need to handle the other points. And I left that guy right there. That was the result of looking at this point. Now I need to look at the vector going from the origin to the lower right of this rectangle. I need to move that piece. I need to take its dot product, calculate its scalar projection, the distance of its projection. So A dot LR represents the distance from this point to this point. Okay? So now I've taken care of these 2 points on the rectangle A. Okay? These 2 points on rectangle A, in the way I've defined it, are really easy. You don't really need to do any dot products. The A... I changed the notation here in midstream. The A dot UL... Okay, let me... I'm going to go ahead. Of when I was doing this, I changed the way I wrote the notation. So let me change that, and then I'll re-upload this onto D2L. Okay, sorry about that. Point, we do the projection for the lower right, we get that point, and then these points are really easy. We don't actually have to do the projections if we're using the scalars as I'm defining them. Okay? So A dot UL is just 0 because it is the beginning of axis 1. And A dot UR is really easy. That's just the length of that side. So you can just calculate that as the length of the side if you want. Or you can go through the process. You can do the dot product and do the magnitudes. You'll get the same answer as if you did the length of the side. So it's a shortcut if you just calculate it with the length of the side. So now we have the 4 scalar distances from this point to those other 4 points. And that's for A. Then we need to do the same thing for B. We take the lower left vector for B. We move it onto there. We do its dot product and project it onto there. And that's where B dot LL is. Okay? Then we need to do the same thing for the other 3 points on B. Okay, and we get those points. Now you'll notice those points are in a different place than a different position than where they put them in the figure. Okay? In their figure, they went perpendicularly across here, and they put the point here, and they went perpendicularly across and put the point there. It doesn't matter. All that matters is their relative positions, not the scaling on them. Okay? And so you'll notice the relative positions of all of the points are the same. Okay? You know what? I think I'm wrong about A.UR. A.UR, I might... See, because A.UR should be in the same position as A.LR. I think my shortcut method maybe isn't right on that A.UR. You should go ahead and do the same process. Yeah. Say that again? Do the dot product, do AUR, which goes from here to here, do the dot product and recalculate, because that point shouldn't be there. It should be here at ALR. They should project to the same position. So I'm sorry, that shortcut won't work. You'll have to do the actual projection of those on there. Yeah. Sorry about that. I did this real quick this morning. So A.UR, you'll have to do the projection because it should fall in that same place. Okay? Now, once you got them here, you just have to, once you have them here, then done step 3. Okay? You need to go to step 4. And this is really important. There's an error in this below image. This image here is wrong. So don't look at that image. Okay? Implement the text here. Okay? So you do this. Basically what you want to find is that there's no overlap between the A's and the B's. That, if you have one of the B's very small and one of the B's very big that encompass the A's, then there's definitely an overlap. If one of the B's is in the middle and the other B is on the outside, you have overlap. They need to be disjoint. Okay? And this wording here works, and I did code this directly. So you have to say, is the minimum value of B, the smaller of those two values, is it less than or equal to the maximum of the A's, and is the maximum of B greater than or equal to the minimum of A? And if that's if that statement is true, you have overlap, which means there's a collision. Okay? So let me go back to here. 8 points, but really one of them you get for free. 2 of them are going to overlap. Okay? And then you've discovered whether there's any overlap in one of the axes. And if there is overlap, you could you could put one of your little brakes in there and get it to jump out of your loops or whatever you have in there. Or you can just continue and check if there's more overlap. That takes more time, but whatever, okay? If you find there's overlap, you can stop. Because if there's overlap and you can be done. If there is no overlap here, that's only in one of the projections. You need to check the other 3 projections, because remember there's 4. You need to look in the directions that are perpendicular to each of the 2 sides of the 2 triangles. So we've just found whether there's overlap for axis 1. Then we need to look at axis 2, axis 3, and axis 4 to see if there's any overlap in them. And if there's no overlap in all 4 axes, then there's no overlap and you're fine. Okay? And so you need to take axis 2 and go through the same process again of what we did. All the other points, doing the dot products and calculating that scalar, and then getting all of your 8 points, all of your 8 distances, and looking at the minimums of B's and the maximums of A's, etc. Okay? So Justin, you did end up going through and doing all that stuff and the loops and the 4 axes, and you got it to work.
Yeah.
Okay.
And I just have a bunch of, I don't know if this is right or not, I have a bunch of if statements, like, because for 6 collision boxes, you have to say, all right, does the first box collide with the second? Does the first collide with the third? Does the first collide with the fourth?
Yes.
And then you have to loop all the way down. And then you have to start with number 2. Does
Yes.
2 collide with 3?
Yes.
And so I just have a whole bunch of if statements.
Okay,
I
and
guess there's probably a better way to do it.
yes,
but-
there is. So you could have a bunch of if statements, all the different combinations, which there's a bunch, but not disgustingly many.
Yeah.
You can go back to be inspired by one of the 2610 labs, the one where you kick the ball and there's the 4 balls, and you're trying to find the distances between all the 4 balls. And you need this, and you could have a nested for loop that loops through all of the 6 things, and check this versus that, this versus that. You can look at sort of that distance matrix where there's ones along the diagonal, and each of the upper and lower are symmetric. So you can look at that, and and you wouldn't look on the diagonal. If I is the same as J, you don't check, and you just do the others. So that's one way you could do it, is with a nested loop going through them, or you could do all your if statements.
Those of us who didn't have the Python version of 2610, can you show an example of a nested for loop?
Sure. They did that in MATLAB anyway, so they didn't do their nested for loop in MATLAB.
That was the thing where we used the tolerances to find the rings around the ball, right?
Right. Yeah. All right. So. X is equal to.
Well, yeah, it's for just all the 4 different.
No, let's see. I'm gonna do this. All right, let's do this. 1, 2, 3, 4, 5, 6. Y is equal to 7, 8, 9, 10, 4. Okay, so why don't we go through and check to see if. So we've got a vector of 6 things. We've got another vector of 6 things. And let's see if we can find anywhere where they're the same number. So that's kind of like what we're doing. So we're going to find any places where there's the same number in both of these vectors. So we can do for I in range len of x, for j in range len of y, and we can, sorry about that, then we can say if x of I equals y of j, then print collision at ij. Okay, run that. So let's see what we get. There's a collision at 0, 1, 2, 3, and 0, 1, 2, 3, 4, 5. I thought it was going to give me 2 collisions. I guess it doesn't. Okay. Right, it doesn't. Okay, so first it starts off looking at 1, where we're looking at x of 1. Then it says, is that the same as that? Is that the same as that? Is that the same as that? And it looks to see if 1 is the same as all of those. Then it takes 2 and says, is 2 the same as all of those? Then it takes 3, is the 3 the same as all of those? Then it takes the 4, is the 4 the same as all of those? Now I guess that's different. It's a little bit different than what we have, because we have 6 things and we're trying to look at all the combinations of them. So if we're looking at all the combinations, then we need to go through x. This needs to loop through x as well. So it'd be more like something like this. This needs to loop through x. Yeah. There we go. Now we're getting the 2 collisions I was thinking we would get. Oh. There we go. Now, did you notice that? That's really insidious. It still runs and it gives something, but y doesn't exist here, but it exists in the workspace because it did before. It was already there.
Is there something you can put at the beginning of this to clear your workspace?
I don't think you can in the script, but you can do it. I have not found it. I haven't researched that really well, but in the IPython console you can do reset, and that kills the workspace.
It automatically did that.
It does not. It does
I
not.
read somewhere that hitting F6 will run in a dedicated console.
Oh yeah, or maybe maybe you can restart a new session or end the session or something. That's right. Will was telling me he did that, where he did something like ended the session.
Yeah, I put something on the top of mine to close all of the plots, so I didn't wind up with 1,000 of them after running those ones.
But there's somewhere you can
Plot under
tools. Somewhere you can.
It says reset kernel at somewhere.
Yeah, reset kernel.
consoles, project.
But I'm not sure. But again, yeah, there's restart kernel. But again, that's not something that's going to happen automatically inside your code. I'm not sure. There has to be a way. There has to be a fancy way that you can do an IPython command in Python code. I just don't know how to do that.
There's one for closing figures that have been opened, but I don't see anything.
I tried to
Yeah.
find one, and when I utilized it, it broke the rest of my code.
I'll have to look into that. All right, so this is.
It went from having a perfectly working, up to the collision detection, and then I put that code in to clear and reset everything, and it would then completely disregard the data that I would load, and
Yeah.
bounding boxes would be all over the place. It just screwed everything up.
So here it found all these ones that they collide with themselves. These are self collisions, which you don't want. So you could avoid that. Say if I is not equal to j and that, then maybe that will gets rid of all the self collisions. You still get double collisions because you're actually checking both the lower diagonal on that matrix and the upper diagonal, so you're getting double collisions. Now, that's not a problem because if you have a collision, you got a collision and you have one. If you don't have a collision, you won't have any, but it's a little bit inefficient. So what you could do here is you could have the second loop start at I plus 1. And then you don't even need this guy. And you won't have self collisions. Okay? So when I is 0, you start with a 0, 1, and then you start looking at the first through all the end. Then when your I is equal to 1, you're going to look at 2 through the end. Then when I is 3, you look 3 through the end. So this is more efficient. It's avoided the self collisions, and it doesn't look at both the top upper half of upper diagonal and above the diagonal and below the diagonal. It's kind of like when you do a bubble sort. Once you sort the first one, then you can start your next loop one farther over, so that it doesn't hurt to stay in place, but it's more efficient. So I guess this is kind of like what you would want to do for checking your collisions, rather than all of your gazillion if statements.
I looked at this like 500 lines of code. I was like,
Well, but you had different number of if statements depending on how many clusters you had. So what you had like if I have 5 clusters, then I do all of these if statements.
Yeah.
If I have 6 clusters, then I do all.
I started with 8, and then I just copied and pasted down to 7.
Isn't that a little self-defeating of the machine learning concept? If we have
Not really. I mean, that's really no different than doing this for loop. It's just hard coding the for loop. But yeah, I mean, it's a little pretty poor style code, but it worked. It worked.
Hammer and nail.
Yeah, hammer and nail. Okay, so that's sort of more like what we're looking at. All right. Other questions? Other things you were stuck on? Yes.
What were you saying about doing this on 4 axes? Because do we only want to check for collisions on the floor, or do we want to check for collisions this way? Or?
No, the axes are the axes of your rectangles.
Oh, okay, I see.
Okay? So you have these 2 rectangles, and there's 4 axes that you need to look at perpendicular to each of the sides of the rectangles.
Gotcha.
Okay. Did anybody see if I posted the YouTube video last night of the lecture recording? I managed to block out the code in there.
I saw that some of the videos had been finally uploaded, but I didn't know.
Yeah.
I haven't had time to look at it.
So luckily, I figured out how to block that out. So. All right. So, any other specific questions? Maybe I'll just stop the recording. I'll come around and look and help whoever needs help. Or any
My other
specific.
question is if for the data that you're going to test our scripts on for not the training set that you gave.
For this project, I don't have anything new.
Okay.
So for this project, you're going to be graded just on what you give me, and there's the rubric for what things are worth what points. So no, I'm not going to whip out any suddenly new training data on you for this one. Not for next one either. But after that, then I'm gonna then the gloves come off, and I'm gonna pull out testing data that you've never seen before for the last.
We're trying to do this for collision detection of other LiDAR data. We would have to check, does it collide on this one? Does it collide on that?
Right. No, there's nothing new going to be for this one. So.